uploaded some of reading materials that I would say be useful in the discussion, because I would say among the electroanalytical methods that we're going to discuss, I think voltammetry is the most important. Why? Anyone? Ba't sa tingin ninyo yung voltammetry yung pinaka-important? Ayaw mag... nawala. Okay, because that's the paper that you're going to write. So in addition to the materials that I have here, I suggest that you go over those materials. Those are the same materials when I was first introduced to this method. Okay. Before Dr. Joey Santos gave us those articles, and I was able to find those articles lately. So I said, oh, maybe it's much better if I gave you the same material, especially when you start writing, okay, the paper that is assigned to you. So today we just have a short discussion about voltammetry, maybe until the working electrode, specifically the carbon. That's what you have. So if you're going to look at the voltammetric methods here, as you could see, I think almost all of them has, we could say, voltammetry. Okay, so we're done with this. Potentiometry. Okay. The main idea is to give this to you before the voltammetry, but what happened is I want you to have at least a knowledge of voltammetry before our reading break, so you can at least have an idea on how you're going to write the paper. Okay, so when we're talking about voltammetry, this is just a group of electroanalytical methods in which the information about the analyte is obtained by measuring the current as a function of applied potential. And in doing so, you must have a conditions that promote what? Polarization. You still remember this process of polarization? Okay. So the one that will promote the polarization has something to do with the indicator electrode or the working electrode. And if we're going to look at voltammetry, this is just the measurement of current as a function of applied potential. And this is under the condition of polarization. And in voltammetry, they said there's a negligible consumption of the analyte. Okay. So when you have voltammetry, it usually refers to a group of electroanalytical methods in which we acquire information about the analyte by measuring the current in the electrochemical cell as a function of applied potential. Okay. Now, there is, we could say, a related method to this, what we call voltammetry, and that is amperometry. So amperometry, we could say, is a closely relation technique where the current is proportional to the analyte concentration. Okay, so that's the difference between the two. Okay, the current is proportional to the analyte concentration monitored at a fixed potential. And a classic example of amperometry is your sugar meter. I think that's one of the success story that we have here. Okay, so in both of these techniques, you only use a very small we could say area, okay, of surface area, just a few square millimeters or at the most, and in some it's just a few square micrometers or less. Okay, this is to compensate the what we call polarization. So in both this method, you need polarization. In potentiometry, you measure the potential when the current is 0, and that means you don't have no polarization. In coulometry, you measure the concentration. The polarization is compensated, and in all of these techniques, we could say the analyte is consumed. But in voltammetry, there's a negligible amount of the analyte that is what we call consumed. Okay, so we could say in voltammetry, there is concentration polarization. So if you're going to recall polarization, can you recall what polarization is? Anyone? Wala na si Carmel, wala na nag-comment sa inyo. So when you undergo when you undergo polarization, you have a polarized electrode. So what happened there? You applied, okay, a voltage in excess that is predicted by the Nernst equation, and this caused redox, either reduction or oxidation, to occur. Okay. Now in potentiometry, as I've told you, the measurements are made as current approaches 0. And in that case, polarization is absent. Now, voltammetry is different from coulometry. Okay, in that coulometry, measures are taken to minimize or compensate the effect of polarization. So there is also, we could say, a concentration polarization in coulometry. Okay, now, voltammetry is very useful in organic, physical, and biological chemistry for non-analytical purposes. So usually when you're talking about voltammetry, you look at the redox process. Okay, you look at the absorption processes on the surface and the electron transfer mechanism. And this is the basis of the paper that you're going to write, because this is where you have the so-called chemically modified electrodes. So you can use this for non-analytical purposes. So that means this is not only solely used for determination of concentration, because that's usually the analytical purposes that we have. Okay. Now, if you're going to look at the history of voltammetry, it is, we could say, a rich history, because before it is what? Known as polarography. Okay, and when it was known as a polarography, what can we say about it? It's a voltammetry at the dropping mercury electrode. But there's a disadvantage of this what? Polarography. Okay. Polarography makes use of mercury, which is poisonous, and the apparatus of it is, we could say, cumbersome. I'll show you a technique, a photo of the hanging dropping mercury electrode. And better techniques has been what we call developed before that. But if you're going to look at the history of voltammetry or electroanalytical techniques, this guy, we could say he's a big guy, Yaroslav Heirovsky. So he is a Czechoslovakian, okay, or a Czech guy who got the Nobel Prize, okay, if I'm not mistaken, in 1959 for his work in polarography, okay. So we could say historically the field of voltammetry started from polarography, which is a particular type of voltammetry that was invented by Hebrovsky. Okay, so polarography, we could say, differs from the voltammetry in that your working electrode is this, what we call DME, dropping mercury electrode. In the 1950s and the 1960s, we could say that's the golden era of polarography. So it's an important tool used by scientists for the determination of inorganic ions and certain organic species in aqueous solution. Okay, however, many of these applications were replaced by spectroscopic method. So hindi pa nga yung ibang analytical or electroanalytical method. It's just the spectroscopic methods. Okay? And they become less important as time goes by, except for some certain application that only polarography is the one that is, we could say, useful. Okay? And this is the determination of oxygen in solutions. Now, several modifications in this classical voltammetric technique were developed, which enhanced the sensitivity and selectivity. Okay? And about at the same time, the low-cost amplifiers made possible the development of relatively inexpensive instruments that incorporated many of these modifications that it has. So there's a resurgence of this use, okay, but because of the nature of the mercury, its popularity declined, especially after the Minamata disaster. Okay, so at one time there are what 60,000 research papers that were developed in literature that says here, but after it peaked in 1973 with 2,000 published articles, it starts to what we call decline. And by 2005, only about 300 papers on this method appear. Okay, although we could say the polarography decline in importance, on the other hand, voltammetry and amperometry, okay, at working electrodes starts to, we could say, become popular. So there is now a replacement of the dropping mercury electrode as a working electrode. And the good thing with this voltammetric and amperometric method, if you couple it with HPLC, they have become more powerful tools in the analysis of complex mixture. And as of now, it's a very important tool in the different fields in chemistry. So you can use it for biochemistry, material science, engineering, okay, and environmental sciences. Because as I've told you, okay, this method is not only for analytical application. It can also give you other information that you can get. Okay, now, if we're going to look at this, what we call voltammetry, as I mentioned earlier, okay, what happened here is there's a variable potential excitation signal that is being done in a working electrode. And this excitation signal, as we call it, they produce characteristic current response, which is the measurable quantity in this method. And we could say this is what? The common waveforms that you observe in any voltammetric technique. Okay, so this is the 4 of the most common excitation signals used in voltammetry. So you have here what? The linear scan. And if you're going to look at the linear scan, what can you say? So with time, you can determine here, apply here the potential you increase here. Okay, so this is the classical voltammetric signal or excitation signal. So what it do, okay, when you apply the linear scan that is shown here, in which the voltage applied to the cell increases linearly as a function of time. And you usually use it in polarography, and this is what we call hydrodynamic voltammetry. Okay, so in a linear scan, the potential linearly increases with respect to what we call the time. And if you're going to look at this, okay, the range of the complete span may be as small as a few millivolts compared to the other. Okay, so it can be as less as a few millivolts to 2 to 3 volts. So we could say it's really a very sensitive technique, or it's going to give you what we call a very good signal. Okay, and the current of the cell is then recorded as a function of time, and thus as a function of the applied voltage. Okay, now in amperometry, the difference of amperometry compared to voltammetry, usually the potential that you apply there is fixed. And you're going to get the current at that fixed potential. Unlike in voltammetry, you can increase the potentials. Okay. Now, for the second one, we could say this is what? These are pulse excitation signal. Why do you think they're false? Anyone? Come on. Ito pa effect pag wala si Carmel. Oh, ayan na si Carmel. Why do you think it's false? Excitation signal. If you read your pulse rate, di ba? Taas, baba, taas, baba. So it's just like same thing here, like a pulse. Or remember in movies you see when patients are fighting for life, usually you see it like that one, right? And then kapag wala na, diretso na lang. Okay? So we could say both of these showed you a pulse excitation signals. And here currents are measured at various times during the lifetime of these pulse. So we can have here what? The triangular waveform, also in addition to the pulse. So here you could say it can be the differential pulse or the so-called, excuse me, square wave. Okay, so both of them are at various time. So the way you do it, you have fixed potential, and then you increase, and then fix, and then you lower, and then fix, and then you increase. So the same thing here, increase at a particular what we call time, and then an abrupt increase, and then increase again linearly, and then go down. Okay, and the way that you use them is based on a type of a voltammetric method. So for the differential pulse, you have what? A differential pulse polarography. For the square wave, you have what? Square wave voltammetry. And I think I have some papers that I have posted about this. Okay. And the last that we have here is the so-called triangular waveform. Okay, so this is the potential is cycled between two values. first increasing and then decrease and then increase again and then what we call decrease. So the process may be repeated numerous times as the current is recorded as a function of time. And the best example where it is used is the so-called CB. Now, before I continue, have you read the thesis that were given to you? Yung totoo. Anyone? Have you read the thesis given to you? Babasahin pala po. Naku po. Mapipilitan ako maging maiksila yung klase natin. Para basahin nyo yung mga journal at saka yung thesis. Because one of the things that they do there is a CB. So the CB usually, it doesn't do analytical, we could say study. It's more on looking at the electrochemistry of the material that you use in modifying your working electrode. Okay, so the way that you're going to do the thing there is either this and this one. Although you will have term like stripping analysis and other terms. That's why a suggestion maybe I just put like a lecture today until working electrodes, and then I want you to read the material that I have posted. So if you can open your Canvas, you can look at it. I said there, reading materials folder. Okay. Now, unlike potentiometry, usually potentiometry, they have what? 2 electrodes, right? In the 2 electrodes, you have the reference and the indicator electrode. Now, for voltammetry, you have here, we could say 3 electrodes. Although early voltammetric system, they were able to perform it in 2 electrode system rather than the 3 electrode, we could say, that is commonly used. So the way the voltammetric cell would look like is there are 3 electrodes that is immersed in a solution of this what we call supporting electrolyte. Okay, so if you're going to look at these 3 electrode systems that you have, so usually the 3 electrodes that you have are the following. So you have the working electrode, where the potential varies linearly with time, usually very small. And then you have the reference electrode, and then the auxiliary electrode. Now the question, in the thesis that was given to you, what are the one that you're studying? Sige nga, mag-scan kayo. Ano yung inaaral nyo doon? Ano yung binabago nyo doon sa system ng study na yun? Because that's how we're going to define this electrode. Ano, diskan nyo na? In our potentiometry, our indicator electrode is our working electrode. So yan yung ano natin doon, yung counterpart. Now, you might ask yourself, paano po sir kapag 2 electrodes lang but you're doing what? Voltammetry. So, alin sa tingin nyo yung matitira dyan? Anyone? Para mag-open session tayo para at least hindi na lang ako yung nagsasalita. Okay? So if this is a 2 electrode system, the 2 electrode system are what we call a working electrode and a reference electrode. But there's a big but. Kasi yung 2 electrode system na yon, yan din yung potentiometric. So ano yung difference ng potentiometric sa voltammetric? The presence of what? Anyone? Polarization. So walang polarization sa potentiometry. So what you need to do if you have an electrode system is make sure that the second electrode is either what? A large metal electrode or a reference electrode that is, we could say, large enough, okay, to prevent its polarization during what we call experiment. So the way that the second, in the 2 system, 2 electrode system that you have, the second electrode should function as both the reference and the counter electrode. So that gives us the definition of the working electrode as what? The electrode in an electrode in the electrochemical system in which the reaction of interest is occurring. Okay? So yung working electrode mo, yan yung ini-study doon sa mga studies na binigay ko sa inyo. Okay? And usually this working electrode, that's the one that has the dimensions that are what? Very small. So that it has a tendency to become polarized. So yun yung ano niyan. Okay? Nature. And the working electrode is often used in conjunction with the auxiliary electrode. Now, the types of this working electrode, it could be what? The glassy carbon, the gold, the platinum, okay, the mercury. That's why if you are using a polarography studies, usually your working electrode there is mercury. Okay, and the one in the studies I gave you, which is the carbon phase. Yes, usually it's the working electrode, okay, with respect to the reference electrode. So the same thing, I told you, ang counter nito doon sa potentiometry is yung indicator electrode. So here, this is the indicator electrode. Now, for the reference electrode, this is the electrode that has the same function as you have in potentiometry. This is the one that has what? A stable and well-known potential. So it provides the reference potential to the working electrode and the counter electrode. So anong pwedeng ano dito? The usual thing, the saturated calomel electrode and the silver-silver chloride. In my experience, ito lang yung nagamit ko. Silver-silver chloride. Okay? So silver-silver chloride in KCl or HgHgCl in saturated KCl if you have the saturated calomel electrode. Now, on the counter or auxiliary electrode, on the other hand, that conducts the current from the source through the solution. So this is often called the counter electrode. used in the voltammetric analysis in which an electric current is expected to flow. So it completes that circuit between the potentiostat and the working electrode. And usually there are what we call two types that are commonly available. And the one that I use is just the so-called platinum wire. And if you're going to look at the instrumentation here, okay, so based on this instrumentation, so this is, we could say, the early voltammetric method that you have. So if you're going to look at here, you will see the three of them here. So usually that's where you have like a glass containers and you have the different electrodes on it in a supporting electrolyte. So what can you see here? Ano yung makikita mo dito? So you will see here the components of a simple apparatuses for carrying out a linear sweep voltammetric measurement. So you could see here, there are three electrodes that are, we could say, immersed in a supporting electrolyte solution. Okay, so the supporting electrolyte, this is a solution containing the analyte that you want to study and an excess of a non-reactive electrolyte. So usually, what can you expect the electrolyte to be? Anyone? Guess. Ano dapat yung supporting electrolyte nyo? Ano yung tawag sa kanila? Anong tawag mo sa KCl? Sa NaCl?
Strong
Your supporting
po, sir.
electrolyte should be what? Anyone?
Strong electrolyte po.
A strong electrolyte. So usually, you want it to be a salt. Okay? So a supporting electrolyte is a salt added in excess to the analyte solution. So the analyte is whatever analyte you want to study. If you want to study heavy metals, so you have there's some mercury, lead, okay, but the one that is present in excess is your supporting electrolyte. Okay, so most commonly it is an alkali metal salt that does not react at the working electrode at the potentials that is being reduced. Because ayaw mo na doon sa in-apply mong potential, nagre-reduce din yung metal doon sa supporting electrolyte mo. You want the only one that is being reduced to be the analyte that you are studying. So usually what the salts do, okay, it reduces the effects of migration and lowers the resistance of the solution. So they usually reduces the effect of migration, okay, and lowers resistance of solution. So yan, we could say, is the four component that you need in a voltammetric cell. So the working electrode, that's the electrode at which your analyte can be oxidized or reduced. Okay, and the potential between the working electrode and the reference electrode is usually what? Controlled. And the electrolysis currents that would pass between the working electrode and the counter electrode. Okay, so the current that you have there is going to pass between the working electrode and the counter electrode. So that's how the instrumentation of it looks like. Another way of looking at this is this one. So you have here the linear sweep generator. Okay, so what it do, you apply the potential out of it, and then there's a current that is generated, so it will be communicated between the copper electrode, the counter electrode and the working electrode. Okay, so once you see there the conversion of the current, you'll be able to get the data. So that's, we could say, the instrumentation for voltammetry. So you have an idea now of what you're going to write. Hello? Kayo nagbabasa eh. Now, let's look at this, what we call working electrodes. So working electrodes, they can come in a variety of shapes and composition. We already discussed the reference electrode. So whatever we discuss about the reference electrode, it's applicable to this, what we call method. So what we're going to do is what we call the working electrode. And the one that we use in voltammetry, they take a variety of shapes, compositions, and size. More often, we could say they are what? Small flat discs of a conductor that are press-fitted into a rod of an inert material. Okay, and I'm going to show you some of the working electrode that is known. So usually this working electrode, they have a potential window that they are applicable. So depende doon sa material na ginagamit mo. And these windows determines the range of potential that the working electrode can be used. However, the window is limited on the positive side by the oxidation of water to oxygen, and on the negative side by the reduction of water to H2. Okay, so it's limited with this one. So this is just what? Anong process to? H2O converted to H2N, O2. When this happen, ano to? Spontaneous or non-spontaneous reaction? Anyone? Anyone? Is it a spontaneous reaction or non-spontaneous reaction? It's not. Okay? So if it's not a spontaneous reaction, that means you're going to apply potential to it. Now, you have to have your potential window in between those two. Okay, on the positive side, the oxidation of water to oxygen, and on the negative side, the reduction of water to hydrogen. Why? Bakit kailangan below or in between ng dalawang to? Anyone? Ba't di ka pwedeng sumobra dito sa isang side at dito sa kabilang side? Because you have water in your system. So if you go over that window, most likely the potential that you observe there, if you apply the potential, the current that you observe there would come from this species. Does that make sense? Ayaw mong lumampas dyan sa dalawang boundary na yan because ang mag-o-oxidize at magre-reduce doon ay yung galing sa water. At yun yung signal na ma-observe mo. Okay? That's why I told you, even when the use of the DME or the polarography decline, it's still being used to study the oxygen. Okay? Napaka-useful pa rin niya. If you're using oxygen. But if you're going to use it to look at the analyte, you don't want to include in your window kung saan nangyayari to. Okay? Now, so these are, we could say, some of the different forms of your working electrode. Okay? So if you're going to look at this, what we call working electrode, the first one there is what we call a this electrode. Now, where do you think is the space for the reaction there to occur? Anyone? Usually, saan banda dito? Yan, yung maliit na yan. Diyan mo lang ilalagay yung material na interested ka. So kung magbabind man siya with the target analyte like lead doon sa binigay ko sa inyo, you incorporate the modifier there. Okay? So this is what we call a this electrode. Now, what do you think is this one? You have a mercury there. That is the HDME. The hanging mercury dropping electrode. O HMDE pala. Because in some book, they put it hanging dropping mercury electrode. But in this book, that's hanging mercury dropping electrode. Okay? And as you could see there, yung electrode mismo yung yung mercury mismo yung working electrode nila. Now, this one, this is what? A microelectrode. Now, look at the size that you have there. Compared to this one, 6.4, this one is just what? 3.5. And if you're going to look at this, it's just so small. Now, this one here, this is, we could say, a sandwich type flow cell or flow electrode. And in a portable potentiostat, the one that I'm planning to leave there, your electrode is just like in one space. So maybe next meeting, I can bring some of them here and show that to you. So all you need is a drop of your sample to determine, okay, the chemistry or electrochemistry that they have there. Ganon siya ka-simple. I don't know if you know Franco. I think Dr. Leah Fernando, she has an instrument that has that capacity. Now, this sandwich type flow electrode, okay, usually it has, we could say, a different configuration. Okay? So usually itong flow dito, meron tinatawag na inlet, outlet, okay? Kung saan pumapasok yung sample ninyo. And then there are what we call connections that goes to the electrode systems that you have. So you can have a dual series cross flow, a dual parallel cross flow. So I don't know if you look at the difference here. Dual series, so dadaan dito, tapos dito, yung sample mo. Tapos meron kang dual parallel cross flow, so the sample will pass through in between the thing that you have there. And then instead of a dual, you can also have a quad that's similar to this one. Okay, and then in addition, you can have this quad arc flow. So what happened here is the arrow that you have there, that's where the sample flow, and this is where your working electrode. Maybe in one of the paper that I did, I look at two enzyme system. One that breaks down sugar into glucose, and one that determines the glucose. I'm not sure. I think the enzyme is galactosidase, and the other one is a glucose oxidase. So what do you think I did? So I have a screen printed electrode. So one thing that I do is a layering. So I put first the galactosidase, the enzyme that breaks down the sugar into glucose. And then the next thing that I do is the what we call glucose oxidase. And I try to determine which one will give me the optimum signal. So the way that I put the layer, one layer is one of the enzyme, and then the next layer is another enzyme. And the other one that I have is sequencing. So usually the flow or the sample would go here and then go out here. So what we're hoping, the interaction of your sugar solution is enough to break them down into glucose, and enough for the glucose to be determined by the glucose oxidase. So the other one that I have is what we call sequencing. So I put here in the first half, the first enzyme, and then in the second half, I put the second enzyme. Now, what do you think the third? What do you think is the third thing that I did there? Mixing. So I just mix the two enzymes into one coating and see what happened. Okay. I forgot already what's the result, but I have a paper on that in Philippine Journal of Science. I think I published it way back 2007. But I did it when I spent 1 month in Austria. Okay, and I learned about this so-called screen printed carbon electrode. We call it SPICE or SPACE. Spice Girls are very popular during that time. So that's the way the working electrode works. Okay, so these are the different configuration of this, what we call sandwich type flow cell electrode. Now you can have a voltammetry wherein you have what? The potential regions for the 3 types of electrodes that you use at different supporting electrolytes. So look at the window. Usually the window that we utilize is just this. In some instance, you go to 1.5. You can look at it in the thesis that I gave you. So look at the difference. So this is what the counter electrode. Okay, the mercury here. This could be a working electrode, or if you put it with the KCl, that is the reference electrode, and then the carbon that you have here, that's usually a working electrode. And kung pinasa nyo yung thesis, what's the one condition that they optimize? Anyone? Tingnan nyo nga. Nag-electrochem lang yata kayo kapag may klase tayo eh. What's the one condition that we optimize? Sige, basa. Sabi nga sa dating daan. Ano yung isang condition doon na ino-optimize sa study? Wala na basa? Siguro kailangan natin ng first drop. deadline.
Sir, yung nabasa ko lang po, fabrication of simple CME.
So ano yung isang condition na ino-optimize doon? Meron section doon, optimization. You can scan through the title. So ano yung isang ino-optimize nila doon na related sa slide na to ngayon?
Deposition potential po, sir.
Is that deposition potential? So that's one of them. But here, okay, usually one, I'm not sure, but I know in most of them, I ask them to look at what is the best supporting electrolyte to be used. Some of them use a salt. So yun yung kailangan yung tingnan when you write them into a paper. Bakit yung isang electrolyte much better than another supporting electrolyte? And it has something to do doon sa electrode system that they use. Kita nyo that one of the things that they optimize is supporting electrolyte. Or maybe the last one who did it, they didn't do it already because it's already established based on the previous thesis that this is the best supporting electrolyte. So hindi na ginawa ng mga estudyante ko. So that's the thing. So the one that you need to remember, voltammetry, 3-electrode system in a supporting electrolyte. And the one that is always we could say, of interest is among the 3 electrolyte is the working electrolyte. And that's where the bulk of research that I have during the time that I was there. I don't know how many paper we did. Okay, Carmel.
Sir, di ba po, sir, na-mention niyo po na salt po yung supporting electrolyte?
Yep.
Pero dun sa thesis po na napunta sa akin, HCl po yung ginamit niya.
Meron silang ginamit na ibang ano. Look at the what we call supporting electrolyte that they have here. They also use what? There's an acid. There's also a base. But in theory, it should be what we call salt. And what's the reason? Okay, I think I listed it down. So the reason is reduces the effect of migration and lowers the resistance of the solution. But, okay, I asked them, what if you have a better, we could say, supporting electrolyte if you have an acid or a base? Kasi noon, ang gusto nila, a salt, usually that has an alkali metal. Okay? Because the other thing that you need to take into consideration, you don't want any of the component of your salt to be the one undergoing redox reaction when you apply the potential. So instead of using what we call a salt, they end up using HCl. Okay? Ilan yung Carmel, ilang electrolyte yung tinest nila doon sa napunta sa'yo?
Sir, yung na-browse ko is time po yung binary niya. Same lang po na
Time lang.
Opo,
Wala yung effect of supporting electrolyte. Kung mga to.
Wala
siguro
po, sir. Kasi parang leaf and stem po yung ginamit niya.
Kasi yung alam ko yung mga huli, hindi ko na pinagawa. Kasi sabi ko, established na naman doon sa mga nauna. So yun na yung gagawin nyo. And the main reason for that is because we're just looking for a particular analyte. So yung parang thinking ko noon, once you see one of them working well, So yun na rin, ganin na rin yung mangyayari sa iba. Modifier lang naman yung pinapalitan. The one that I think, what do you have? Ang mga nauna kasi is mga banana, pinya, feather, pero lahat yung mga napublish na eh. Sila yung unang batch ng student. And they are, we could say, the better students doon sa batch of students that I have. Kangkong, yeah, isa yan sa mga nauna, I think, yung kangkong. And I think that's more superior than the other because I asked the student to look at kung meron bang effect kung ang kangkong leaves or kangkong stem yung ginamit nila. Because the idea that I have there, so usually kangkong, which is that Ipomea something, they could develop some metal binding materials kapag in-expose mo sa environment na merong metal. So, yun yung parang hypothesis namin noon. And I told the students, most likely the stem has a much better binding site compared doon sa lips. Parang ganun yung theory. Because I asked them, bakit mo ginamit yan as your what we call modifier? Okay. And this brings us to the working electrodes. So usually the working electrodes that we have, it could be a metal, silver, gold, and platinum. So what can you say about them? All of them are the so-called noble metals, right? In some instance, you can have what? A nickel. Okay. And then there is what we call mercury. Now this one, this is a disulfide thing, but it's not a metal. Okay. So mercury is the other one. And then in some instances, we can also have what we call carbon. So carbon, they said, is more complex than the metal electrodes. You have to take into consideration some of the sp2 carbon, and they varies in terms of their conductivity, stability, hardness, and porosity. Okay, so usually when you look at the carbon microstructure, especially yung graphite, they are inherently anisotropic. So what do you mean by anisotropic? Anong ibig sabihin yan? First time nyo ba marinig yan? So, I think similar dyan sa tinatawag na isotropic. Ano ba ibig sabihin pag may word na iso? Like isothermal. Ano ibig sabihin ng isothermal? Di ba the same temperature? So, yung anisotropic is what? Usually, iba-iba yung properties niya depende sa direction. So, if you're going to look at this, so you have the H plane versus the basal plane. So, iba yung, we could say, property niya depending doon sa direction. Okay? So when you say anisotropic, these are materials whose properties are directionally dependent. So they change with the direction of the object. Okay? So yan yun, we could say carbon structure. So the one that they usually look at here is the so-called HOGP. Yan yung tinatawag na highly ordered pyrolytic carbon. Okay. So they found out that the properties of the two planes are very different. The capacitance, the basal plane is less than 1. while the H plane has 50 to 70. Okay. The absorption with respect to anthraquinone, the basal has 1, but the H plane has more than 150. So yun yung tiningnan nila doon sa carbon microstructure. Okay. And they found out among the common carbon electrodes that they have is the HOGP, highly ordered pyrolytic graphite. So this is made by pyrolysis of the light hydrocarbons at 800 degrees Celsius, then treated at high temperature and pressure, annealed at 3000 degrees Celsius. So they have a weak interplanar bonding, so they can be renewed with adhesive tape. Okay. And the one that we usually use is the carbon-based electrode. This is the polycrystalline graphite electrode. So all of you have what we call the CPE. Okay, so this is a control porosity of graphite material by filling pores with inert liquid carbon paste is graphite with nudule. If you're going to search the word nudule, okay, it's either nudule o yung tinatawag na mineral oil. Yan yung meron doon. Okay? So it's mixed with nudule or hexadecane. Wala kaming pera noon, so we cannot buy hexadecane. So we just use nudule. All you need is a drop of nudule. And then you mix the graphite carbon. This is a carbon powder. And mix it with the modifier that we use. So small amount of modifiers lang yung ginamit namin. Okay. And then we pack the paste doon sa well. So usually meron kaming Tetra Pak straw. You familiar with the Tetra Pak straw? May Tetra Pak pa ba dyan? So we put the copper wire and then we put a small space there. Doon namin nilalagay yung carbon paste that is mixed with nudule and the modifier that we use. So carbon paste, they are easily what? Modified. So all we need to do, kung may functional group, yung materials or modifier na ginamit namin, most likely, we take advantage of that functional group to bind with lead. So may idea na kayo kung anong susulat nyo? Ha? Yung iba, si Carmel lagi nasagot eh. Anyone? Yung next time mag-post tayo, yung merong photo lab. AI-generated photo lab. So that's the idea of the working electrodes that you have there in your system. Okay? Yan yung ginamit natin. But there are others, polycrystalline, we could say graphite electrodes. One is the spectroscopic graphite electrodes. Now, why do you think we don't use this one? Because it's more expensive compared dun sa isa. Wala kaming budget during that time. And to tell you frankly, we did it with everything, with funding from our own personal pockets. Okay? So ganun kahirap yung magawa ng research noon. So when you have a spectroscopic graphite electrode, just like the spectroscopy reagent grade, the spectroscopic grade reagent, mas mahal sila. So here you have rods with low metal impurity used in emission spectroscopy. You can immerse it in molten wax, ferrocene or parafilm, and then place in the vacuum polish end of the rod. Hindi namin, doon tayo sa sa one with nodule, yun yung ginamit namin. Or you can have a graphite composite electrode. So you mix the graphite powder with a suitable filler that hardens. We don't use that. Okay. Or you can have a glassy carbon. So these are high molecular weight carbonaceous polymer like polycyclonitrile phenolformaldehyde resin. So the polymer is heated to 400 to 800 degrees Celsius, then heated under pressure at 100 to 1000 to 3000 degrees Celsius, hard and highly disordered. Fortunately, we don't have that. We stick to this one, the carbon-based electrode. You can also have a carbon fibers made from acylonitrile PAN drawn into filaments during curing. So there's a lot of carbon working electrodes that you can use, but the one that we stick is the CPE. So this is how they would look like. The illustration of the carbon fibers, the side and the end view. So this make it what? Anisotropic. Okay. So if you're going to look at them, they don't have the same properties. Okay. They have different properties depending on the direction. So you have an ordered on ion fiber versus a disordered random fiber. So that's the difference that you have. So maliit lang yung electrodes na yan. And the modified electrodes that we have, so you can have a glassy carbon electrode and then you modified it with something. So you can do some reaction. Irreversible absorption, covalent bonding, coatings, enzyme, and sub-assembled monolayers. This is a very big field, SAM. The experience that I have is the sol gel. You're familiar with sol gel? Anyone? Sino sa inyo nagtitesis sa inorganic? Guys, ano ba ginagawa ni Ma'am Daang? Anyone? Alam ko, hindi ko alam ano mga research ng faculty natin dyan eh. Or most of you are just starting your MS. That's why you cannot answer the question. So in the sol gel method, it's just like you're preparing glass-like property. So it starts as what we call liquid, and then it becomes solid. And again, this is a very good field in research. I have experience on it. I did it during my PhD. So until dito na lang muna tayo ngayon. So working electrodes. And then we continue. So open session. Yun lang, pakita kayo. Ganun eh. Papatahin ko na yung recording. Or maybe I'll post it. So question.